G'day guys. Had some guys ask about the grounding on these detectors. This one here has come in for upgrades, and when you go to pull this apart, you've got your sticker here, which if you peel it, it'll break underneath and it'll say basically that it's been tampered with. It's got a rattle in this one. Hot melt glue most likely. But to pull these apart, there's two ways you can do it. I've done a video about you can get rid of the sticker with isopropyl alcohol and retain it if you want, or the other way of doing it is just cut it down there. Just cut it along the seal with a knife. Or how about we do both ways first? And what I'll do, I don't want that. I might as well use this, the big long T10. It's total overkill, but actually it is overkill. I don't need it. You need that when you do 6000s because they've got deep screws. What I'll do is just use a small one here. Otherwise it looks a bit strange. So what we do here, make sure the drill goes around the right way. Take the screws out. When you do this, make sure that the bit actually goes in to the into the cutouts on it, or else what will happen is you'll skate off across the front face of the detector, and you don't want to do that. So there's your screws from the back part. Now if we want to do this, what I would do is we'll give it a go with isopropyl, just see how we go. It doesn't hurt anything, but you just want to get it like so you can actually get in there. Don't pull it because you'll wreck the sticker. So we'll just keep it like that for a bit, and we'll just spray it with some, you've got to get it under the sticker, so that's a bit of isopropyl. You can flood it on there, it's not going to hurt anything. And even with a bit of wiggling and jiggling like that, if it gets in there, tip it back and forth, and you can see the sticker coming away already. So normally you just cut the thing. I mean, these are all out of warranty anyway, so so be it. But if you want to get it, just a bit more in there, let it just drop behind the sticker. Yeah, it'll just fall off by its own weight. Don't pull it, because if you pull it, it'll destroy it. As you can see, all the writing's intact, and we're about halfway down. I'm just touching it, give it a little bit of an extra push. Just keep it wet with isopropyl in case it dries off. This is one thing you don't want to rush. If you rush it, you'll leave the lettering behind. Really, it's hanging by about a millimetre. So well, that bit's off. Now it should just fall away. There you go. And that is how you save your security sticker. So when you put it back together, the isopropyl will dry away, and just push it down, it'll stick back where it was. So you don't want to hit that and damage it. So the other thing we've got to do now is go take off the back. What we do is a little bit of glue on there, touch it because it's usually brittle, and off comes this part, and there's your glue that was holding it. So just tap the mylar or the glue and it'll break the seal. Don't bend that and destroy it. Put it somewhere safe. So I'm going to put it in with its screws. Now, because you've done this with the sticker, you've got to make sure that you don't wreck the sticker. So the thing would be now, get the drill very carefully. Jesus, there's a lot of dirt under those screws. Okay, screws in there, and just push the board a little bit. Give it a bit of a wiggle at the front. And there's that bit of glue that fell out, and it would help if I concentrated and actually undone all the screws, wouldn't it? That's the trouble making videos. Okay, in there, and now you just do this. Hold the board so it doesn't do a backflip or anything, like so, and that's it. Put this away so you can not damage it. So we'll put that up high, somewhere up there. And that is your board. When you get to this part here, you can see the glue on here. Just touch it. See, it just went, I'm being very, very light fingered. There, see that? And it just broke away. Now, get these things off, put your finger in there, grab it hard, and a millimeter wiggle left and right like that, and lift, and off she comes. Don't wrench these that way or do anything brutal, because you'll wreck it and you'll have to put a new one on there. So that is one of the things that has to be done if you do that. So we've got the glue there, we can get rid of that. I'll get rid of the drill driver, and here is our detector. Now, the bits we want to work on are all under the wires here. And what do we got here? We have this big ferrite, okay? And my cutters are cut. First thing you do on these ferrites, it has some cable clips. Just cut them like so, and they do go through the back of the board here. To make it easy, just cut there as well. Don't cut the parts. There you go. It's all covered in white paint, so white paint flicks off when you cut it. Push them through the holes. Try to push them through the holes. But anyway, grab hold of it and yank it out and throw it in the bin. Make little cable ties can go down there. Now the next thing you want to do is you want to get the ferrite, which is hot melt glued, off the circuit board. Isopropyl, each side, a little bit of isopropyl. Let it just sit there for a little bit. It'll just break the surface tension around where it touches. What I do, you can get something like this, or a rod or whatever, and very gently, without squashing the wires of course, and don't put too much tension on it, just like that, and it will pop off the board and leave the glue behind. So if you want to get rid of the glue, there's probably enough isopropyl on there. It probably would have loosened it. Grab it, and there it is. That is the glue that was holding the ferrite down. This gives you a chance to straighten out the copper wires. These things, they are, because of the vibration, traveling in the car, whatever, these wires go very, very stiff. And it's probably also the plastic on the wires is probably you know, maybe it's dried out a little bit too. It's very stiff, these ones, and you've got to be careful that where it connects to the board, that it hasn't done this and breaks all the strands. Just if it does that, just chop it, clean it up, and resolder it. So that is how you pull one of these apart. Okay, this blue wire here, that is connects to the transmitter. That's your receive input line, and that cops the flyback voltage. So you do have 185 volts odd on that wire there. If you're running a mono, it will also be on this purple, or is it violet? And some detectors have different colors. They must have run out of wire. So at various stages, you know, for mono on there, you'll have high voltage on that. And this one here is your signal ground. Now that does connect in the connector to the two pin 1 and pin 5. And the reason it's done like so is that it keeps this, you could connect all this circuitry here to this big black wire off the coil. It's the same potential, but what would happen, all the noise and whatever else is going on will get into the low level. So this is actually a separate ground, and it just stops the noise from the transmit switching getting into all this and making it a little bit unstable. So that is that. You got where the signal comes into the detector on this side of the board, because it's two channels, remember, two input channels. The first port of call is that one there and that one there. They are the MOSFETs, low capacitance, low on resistance, 2SK1334s. They're the things that usually blow up in these detectors if you do silly things with the coil, like loose connector, on and off, you generate high voltage. The clamp circuit may not clamp it quick enough, and you'll avalanche these and they'll start generating smoke. So it goes through these two, and if these fail as well, it also takes out the N MOSFETs, which feed the op amps here, which it's weird, it's not symmetrical. You think that, oh, that'll be one there and that'll be one there. It's not. That is for that op amp there, and that one down there is for that op amp there. These other things are BAV99 protection diodes. So you'll have a protection diode there and a protection diode there. So, you know, like I say, it's not, even though it's two channels and it's meant to be symmetrical, the layout is not symmetrical. Electrically it is, but the layout's not. The other thing too you've got is some BF 908s, if they can still get them. Maybe they bought millions of them, but you can replace the BF 908 with a BF 998. The 908s were made by Philips or Nexperia. They have gone out of production years and years and years ago, but there's plenty of BF 998s. They're very, very close, and it doesn't make any damn difference anyway. You can put them in there to replace them if you have these things smoked. Because if you have a look on eBay or anywhere that sells these secondhand, the price has gone ridiculous because they're not available. So what I've done, I've run around and bought up hundreds and hundreds, or actually probably thousands, of the BF 998s, both brand new, and some of them from China are actually pulled off boards. But the thing is, they do it properly, and they're very, very cheap. You can get them for like about 4 cents each, and you get a hell of, and they're very easy to test too. You can test it with your multimeter in diode test range. If you actually touch the two gates, it on my particular multimeter, it goes in conduction and out of conduction, and it actually says that that's functional, right? That's how I test them. and it'll make a sort of well, normally you get the tone. It beeps with the tone, but it's the tone going on and off. It sounds like it's modulated with, oh, it's actually modulated with whatever your power is on your workbench, so 50 or 60 hertz, depending where you are in the world. It'll sit there and go buzz, but at the tone, so it's modulating the tone in the diode test or continuity test. So that's how you tell. Just that leakage is turning things on. So yeah, that's one quick way of doing it. So yeah, you can, if you do have a avalanche or basically a problem taking out the 2SK1334s on these particular detectors, these are all N-channel FETs again, connected round the other way, because you've got the negative 200, well actually, sorry, you get the positive 200 volts odd 185 coming in, so they block that from getting in here and blowing everything to pieces. But still you have the transmit voltages 5 and 15. That will still go through these FETs because they are, then it'll go through the body diode, and then it will go onto these, into here, like where these two other ends are. They're connected around the wrong way. Well, it's not really, but so those voltages can't go through the body diodes and into the op amps and fry them. So you just take notice of that they're N and N. On the earlier models, on the GPs, they were N and P, and they had different gate connections. These are all just paralleled up. So it's basically slam, 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 and you're just relying on the these being turned off and the body diode not conducting the plus 5 and 15 into the inputs of those AD797s and frying those, because it will. So there's your damping resistor. That's meant to take down as much as possible within reason of the flyback pulse, the ringing, and that most of it's cleaned up by this MOSFET here, and this capacitor acts as like a reservoir with a feedback network. The MOSFET's basically acting as a variable resistor, and it just wants to keep the voltage whatever it's set at. Usually it's about 185. It can be higher and lower. It just depends on tolerances. So if you measure, say, on the back of these diodes here, or even be careful across this capacitor that'll send you over the chair backwards. If you actually get onto those contacts there, they are covered with white paint, but that's 185. I don't think that passes the test. Like I said, all the new detectors have warning, high voltage. These don't. So, in my opinion, I'm pretty sure of the regulations, but I might be wrong that it's actually mandatory to have anything labelled it's high voltage, and it's not. And it should have a warning on the detector saying that, yeah, if you open it up, you might get zapped, but no warning. But it is on the, there's no warning on the other detectors, but it does have an area, and it says, it's got the cross hatching, and it says high voltage, it's got HV there. So you know not to stick your fingers in it. This one, if you did and grabbed the board, and I've done it, right? I did on an SD2000. I grabbed the board. The bleeder resistors had gone open circuit, as they always do, and I got that 185 or whatever it was. I reckon across my, I think it was across one hand, and I was touching something with a screwdriver with the other, and I copped the whole brunt of discharge, and I had to sort of stop and think that, am I still breathing? Heart still going? You know, it was that severe. DC bites. AC will tend to kick you off, but these are all, you know, that capacitor there, 185 volts stored in it, whack, and you know about it. So be wary. You know, we could get the black texture out, and all around here we could cross hatch it. all this section with that high voltage, there's a, I think it's a 4093. Here is it, or 40106, one or the other. One's a quad and one's a hex, but I haven't bothered mucking around with these for yonks. This never usually plays up, and if it does, it's one of these little transistors in here. Your regulation goes out, and it usually is one of these. I think it's an N and a P around here somewhere. Can't really tell. Might be that one and that one. But anyway, what happens if they play up? The regulation goes out. But the other thing that can happen too is that MOSFET, which is there, that's where the legs are, also high voltage on that, can go short circuit and open circuit, depending. And when it goes open circuit, you'll measure across the capacitor or from the diodes to ground, and you'll find something like about 240, 260 volts there. And that's getting quite hairy scary. But the thing is, what really amazes me is that even though you had the detector on and it's carrying on, but it's still, to get that voltage, it's going to be transmitting. And the flyback has to be at that level. And the input FETs survive it. So they have a lot more headroom than the 200 volts they are rated for. It could do damage to them. It could make them go noisy, and you might not be able to tell. So if anything like that does happen and you end up with massive voltage rails on this reservoir, basically energy catch system, it feeds it back into the battery through the other inductor anyway. But yeah, just be wary of the high voltage. If you lose your voltage rails, let me see if I can go from memory. I can. Yep, okay. This one here, that's a 5-volt Schottky diode that supplies 5-volt rail for the transmit. This one here is a 15-volt for the transmit because you've got dual voltage, remember? Dual voltage technology. So yeah, for the big pulse, the long pulse, 5 volts. For the short pulses, 15. And yeah, what else we got? There's some other interesting stuff on here too. Yeah, I'm gonna have a look at this. I don't usually get right into these. These things usually don't blow up. Normally don't blow up. They're very, very good. If I remember rightly, that. Yeah, normally they blow up on the GPs. There's a lot of stuff on the GPs that blow up, and yeah, I'm sort of used to it. Where's the power supply on this? It is there, under there, here. So that there, that is just all the. It's a 40. It's a 744040 for memory. It's just got all the ins connected together and all the outs connected together. I use it as a driver. It's just a lot of current, but yeah, interesting way of doing it. Don't worry, I've done it myself. But to get more current, to drive the power supply MOSFET on and off, that's how they do it. They just parallel all the ins and outs and drive it there. That's the ADG 333. That's basically switches all the functionality in the detector, turns MOSFETs on and off and whatever, depending what voltage levels. This thing will work in negative voltage, positive voltage. So it goes below ground. That's why they use it, I would say. But yeah, that is basically the guts of it. I could go through and say that's that, and that's that, and that's that, and that's that, and that's that. But I don't really want to, because it is time consuming, and there's tons and tons of components on that side of the board as well. Yeah, but the main things that blow up those MOSFETs, that MOSFET, and if you lose all that, just be wary that it will take out most of the stuff in here. And if you try and one thing I'll make note on too, some of these boards, the lamination is not what I would call super laminated. And you got to be careful that if you don't heat it up enough to get the parts off, and a slightest tug will lift the pads off, and it's a disaster. So you've got to be careful. I've done all the hard yards on this, so I know not to do it. And the other thing with these two, if you ever wanted to know, if you're looking at if you want to find an old 4500, not the new 4500, what you'll do is you open it up and have a look. You'll see there's capacitors and inductors here, and there's a row of capacitors here. The old 4500s don't have those. I'm hiding them. They don't have them, right? But the 5000 4500, whichever software goes in and whatever little part changes, have these here. So usually, if you open one up, you'll see that, you'll know it's a 5000. But to the best of my knowledge and to the best of my memory, that the later 4500s were actually built on the 5000 board. If it is a 5000 board, or is it just a general purpose board? I don't know. I didn't design it, so I'm just saying that the best way to find out if it's an old one, usually with the higher gain, more gain in the front end, it won't have, this is only on a 4500, it won't have that, and that. What they've done is this here, which is, as far as I know, in my opinion, to do with their SETA system, and these supply higher voltage rails. Well, there's a couple of extra bits under there as well, but it supplies 8 volts instead of 5 to this chip here. I think it's actually asymmetrical. It might be -5 and +8, whatever it is. Like, when you're working on these things, you just know it's like fully automatic. You don't actually think, oh, it's that chip there, and I should be getting that there and that there. It's more like, poke, and even just glancing at them, you just subconsciously know what you're meant to see, and you don't even really take much notice. It's just like, oh yeah, oh yeah, oh yeah, oh yeah, oh that's wrong, and then you'll go and hunt out why. But yeah, it is difficult for the average tech to work on these because it's all covered in white epoxy type paint, whatever it is. You look at it and you're thinking to yourself, well, if I could see the track work, I could sort of visualize a partial schematic in my head, even though there's lots of through plates and internal tracks and whatever else, and you'll never work it all out. But it gives you an idea, especially, where, say, the power supply for these chips, plus or minus supply, where's it go? Well, you see those caps next to it, you know damn well that's where it is, because we just know that. You don't put that capacitor over here for that. It would cause instability. So all the capacitors go close. A lot of these are here. Also, the caps are close. But then again, you have capacitors here, which is part of a filtering network. And all here, then goes your signal. You got these two caps here. You got a 3.3 volt supply, plus and minus there. That one there, you got a pretty rough and ready plus or minus 5 volt supply that powers all these. When you're getting into the op amp stage here, where I said it had the separate ground, the rest of the grounding is there's no ground supplied to the input stage except through this yellow wire. And if you haven't got your coil connected in and the two earthing points on 1 and 5, there's no ground. to your input stage, and it'll just float high. So everything will have 5 volts on it. You'll go, what's going on here? So that is one thing to look out for. If it doesn't work, it might be the wires come off in the coil, in the plug. So be wary. Just make sure that this point here or any of the grounds, usually you can take it off pin 4 of the BF 998 to ground, or that's ground. And a lot of through plates here aren't ground. They go to the other supply. They're all everything else, but all the low level noise parts, like especially the BF 998s, which basically go across the inputs of the op amp. It just speeds up settling time, as far as I know. It does work without them, but then what you have to do is you've got to put a 33k resistor across the non-inverting inputs to ground and just leave it there. But it does work, right? So if you haven't got them, you can make it work with just supplying it with some bias current that way. Because you got to remember, these things are turned off and on the inputs with the MOSFETs. So the poor thing sits there and it goes, okay, I'm on, and here comes a signal, and now I'm off. Where do I go? So it does need some biasing to ground. Otherwise, they'll go completely bonkers. It's a good word to explain a non-input terminated op amp. It may go high, it may go low, it may do everything, but when the receiver comes back on, it might be stuck up on its near its positive rail. Then it's going to come all the way down, settle. All op amps have a settling time, and if it extends, not likely, but if it does extend into the receiver time, you're going to have this ripple on your receive signal. So that's why they got them there. It just speeds things up and keeps everything under control. And if you have a look at a lot of other detector designs, a lot of them do not have these dual gate MOSFETs sitting there. The reason why they use dual gate MOSFETs, it doesn't have any great loading effect on the devices. And you can go in and look at the transconductance if you really, really want to have a look at why they do it. I'm not going to go into it, but it does. It gets rid of a capacitive storage charge. I said I'm not going to go into it. You don't want to know. Sorry, it's boring. But the other thing too, if you ever look at your waveforms in this thing, and it looks horrible, and you get a lot of ringing after the transmit, ring, and it just starts off that big and fades down like that. Guys, there's your culprit there. That's your damping FET. We're switched in and out of circuit as need be, and that can go open circuit if that's not getting switched on. Also, that's driven by the ADG333. And if that fails, sometimes this does fail, and when it does, it actually gets red hot. You feel it, you go, bloody, you can't touch that. So, but that drives a lot of things. Also, occasionally, right, when these go down, if it goes into the gate, if you get high voltage into the gate, it can blow that up, okay? That thing there. It'll sit there and get hot. They always fail and get hot. So that's what that is. But yeah, that's the other thing too. If you've got ringing on your circuit, always check for that. Yeah, nah, I don't know. I don't want to go into too much detail on it. I'm just trying to pick out the main things that, you know, if any of you are technically competent, want to have a go at repairing your own detectors, yeah, you know, these diodes here, these are on the transmit lines. They are to try and belt down a little bit of high voltage leakage, and yeah, they can go short circuit. The thing is, when they can go short circuit. And I'll tell you something interesting. There's a little one in here. There, that is a tiny diode, and no one ever worked out what it was. I can tell you what it is. It's it's called an SOD23 package, and it is 33 volt Zener. So that's that little thing there. That can go short circuit. These can go short circuit. Even these diodes, there's one there, and there's two on the other side, which isolate the two MOSFETs from the coil through a voltage drop each. Because you don't want to turn your 15 volt one and pump the 5 and the 5 pump and the 15 as they turn on in sequence. So they use a diode isolation, and the other end of the diode here, there's actually two up the top, one here. They used to have two here, but they realised you don't need four. As you can see, it's got the oh dear, I'm going to sneeze. Don't sneeze. Nearly sneezed, but yeah, you can see there's a provision for a diode here, and all heaps of these, the old models and that had the four diodes, and then they realised that was a common point through one diode back to the reservoir capacitor and that MOSFET that lives there. So they saved themselves a diode. So what I will ask though, and it beggars the question, doesn't it? Who put four in there when you only need three? Yeah, well, maybe for longevity, but yeah, you work it out. I'm just pointing out the obvious. So that's that. The other thing goes wrong with these things too. Mylar strips, never usually the front one. Don't ask me why. I think it's got such a beautiful curve on it or something that I don't know. It just doesn't break the tracks in the Mylars. The back one, yeah. The main thing with the back one, and I don't want to grab that up there because I don't want to grab that. I'll grab this. This is it. This is the back part of the detector. Now, the early detectors, when I made mention of it, these things were screwed directly down onto that foil, and now they've got a metal plate in there, so it doesn't crush the plastic and go loose. Because when check these on your detectors, guys, because if this here, not the inner part, that's always got a bit of a wobble to it. If I do that, no, it's not wobbly. A lot of the old ones, they wobble a little bit. They shouldn't wobble. But the metal bit here, if that is loose in any way, what that'll do, not that you can see because they put a bit of rubber there. You can stick there for the time being. What happens? You can see the where the mylar is here. If these pins, which are soldered through the mylar to all the tracks, if it does this rotation, it goes snap, 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 and breaks all those connections. And if you have intermittent audio, intermittent power, all sorts of weird stuff happening, even in some cases, the detector, that's usually to do with broken tracks here on the data lines, but if it doesn't retain the last previous settings and just reverts back to a default, which you didn't set, it'll be broken data lines in here, and usually it comes down to the mylar where the metallized parts are here. They develop, well, when they go in the connectors, they're under pressure, and vibration holds the little bottom bit, say it holds it very, very stiff, and the rest of it can vibrate. And it's gold flash copper, work hardens, breaks, and you get little hairline fractures right in the middle there. And what you can do is, if you're very, very careful, you trim this by 1 millimeter. So it goes in further and the cracks are below the connection points. So that's one way of saving yourself buying a mylar. But also check around here for you know, it looks dry joints, so it's all coming away or something of that nature. But with this additional metal plate here, that should not happen. So, and yeah, I don't know. You know, I'll tell you, that piece of rubber, the only thing I think that's for is because all this stuff juts out. It's sharp and metal. It stops that if it's gotta look at the distance. Yeah, it stops the back of this pushing against the metallization here on the plug and wiggle, wiggle, wiggle and wear through and touch and blow your detector up. So that's probably why they've got this on there. So be wary of that. Even a better way of doing that is, like I've said, to keep the vibration out of the mylar, because that's the wobbly bit, right? Stick that on the mylar in line with that. So if you want to be really clever and have more longevity to your detector, what I would do, I'd do that because it would act as a dampener. So it would dampen your any vibration into your mylar, and it shouldn't wobble as much, especially high frequency vibration, which is usually the worst. That will break these. So you could do that and see if it does fold back, it's still protected, it's no big deal. Or if you want to, put two on there and put another one here or whatever, I don't know. But you can do stuff like that. It's not hard and fast. What else? What else? What else? Oh, there is another thing I was going to say. If you drop your detector, you drop one of these, okay? There is so much impact that with my pokey device here, see the circuit board is screwed down hard onto the plastic, okay? And all around 4 screws, it's screwed down hard. So if you drop it, a lot of energy will go through here and it ends up going through the display. The display's connected, but because there's lots of layers in the display, how it's made. I used to make displays, by the way, and that shock wave can actually break the seal on the display or break the glass. Also, where the wires go through, it goes onto some like a beryllium oxide conductive strip goes into the display, and it can shatter under the epoxy because only glass, two little bits of glass, and the back bit where it connects is one piece of glass, very thin, like a microscope slide, thinner than that actually, and it can break really easy. What you want to do, guys, take these screws out, okay? And if you really, really want, what you do on these stalks where the screws go in, get some tiny, tiny little rubber O-rings and put one there, so the screw goes through it. It lifts the board up a little bit, but it doesn't make any difference. You lift it up probably, I don't know, 0.5 millimeter, not going to do anything. So, and then put one under the screw head where it goes onto the board. So even though it'll be rubberized, if you drop your detector, it is more likely than not to have a break in the screen just by having the impact absorbed by rubber. You could just do it on the top if you wanted to, but it really isn't the best way of doing it. You want to do the top and bottom of the board. And the thing is too, when you put the screws in, don't screw them down super hard because that will get rid of all the rubbery movement, and you want to leave the screws that they're tight. It's common sense. You've got to feel it with your finger as it bites. It's a self-tapper, it'll bite into the plastic. But you've got to feel the tension to know damn well it's not going to fall out and go and drop into the circuit board. Probably won't do anything, it's all covered in white paint. But you still don't want that to happen. So you just feel it, common sense, and if you are worried, get something like a little bit of non-acidic silicone, dab it to the board from each screw, so the thing can't turn by itself or with vibration. yeah, so that's a fair bit about this. Anyway, this one's in 4 full upgrades and modification. So I'm going to have to strip it and redo it all. And the other thing too about modification, I was actually doing this because I was trying to get the maximum punch out of the detector I was doing for the drag coils. You can get a lot of gain. You can put a lot of gain in. This is what happens. I'll tell you what happens. Okay. People say, I want as much gain as you can shove in the thing. And I go, no, you don't. You really don't. But the request is, look, I want to go deep and, the whole story. But because you can adjust everything, you can say, okay, but what happens? This is one thing that happens. If you put on, I've got to be careful what I say here. If you put or connect to the detector a crappy coil, and by saying crappy coil, I mean one that has too much capacitance in its construction, either interwinding capacitance, which is the winds themselves, or the shielding to the windings. It's anything that does this is a capacitor, right? As you do this, more and more and more capacitance, right? Less and less and less capacitance. That's how it works, right? And if you've got something like wires, even wires that go around, even touch circuitry and that, between each wire winding and all the other wires, there's capacitance. So you got to get things spaced. Well, I'm not going to show that because you'll know who made it. I was going to point something out. But what happens is people want these detectors and they go, oh, I want all the gain. What happens? People crank the frequency up and they turn the gain all the way up. They put a crappy coil on the detector. I won't say what sort of crappy coil because I don't want to, because it'll cause problems. And the detector will desensitize straight away. And it'll still have a little bit of burble, and people think it's working. It's not working. I always say, you always want a test target, small one, throw it down the ground, and make sure the detector's actually working and picking up the target. So the problem isn't normally it's not normally a problem with mono coils. It is especially double D coils, right? Because you can crank the gain up, and just the way these things are made was, well, I've seen them, well, not saying anything too much, but the way they're made, they do have well, if you look at my last video, I probably explained a lot to do with it. I just don't want to say the wrong thing, and then people will say, oh no, their coils are like that, he said, and then I'm in the poo. But coils that have a lot of capacitance are not fast. They can't do transitions fast. And when there's a lot of capacitance there, you're putting up your speeding up your timing for your detector to have the receiver turn on closer to the transmitter turning off. This gap gets narrow, and then you've got this capacitance causing this bleed over effect, and it just goes straight into the receiver and goes dead as a dodo to a degree, within reason. And both clocking it too fast and running too much gain. And a combination of the two will cause that issue. So I'm thinking to myself most of the time that I do these detectors in such a way that it will work with a DD coil, no problem. But then I get the people who say, but I want all that extra oomph. And I say, like, yeah, you're going to get yourself in trouble and you're going to blame me for it. So I'm very reluctant to just crank the living bejesus out of them, because you're going to get some cruddy coil, and some monos can be a bit, if yeah, some, and you just got to be aware of it. You know, I, I just can't say what's what. I really can't. Even with our big drag coils, because it's not the interwinding capacitance that is the issue. It's because the damn shield is so huge that you get shield to winding capacitance. And we have to be very careful how we make it, measure it, make sure we space it properly. Because people who want to use big coils and they want their detector to be, um, you know, the almighty monster gold nugget machine, can get themselves into trouble by having a mismatch of coil to detector. So there is that to take into account. So yeah, the one we just did, it will work on anything, and I've done other stuff in that detector to mitigate the effect of bleed over into the receiver. It still goes fast, but the guy isn't interested in, you know, 0.001s and stuff. He wants big stuff, you know, big huge coils. He's using massive coils. David's made these coils, and they're absolute monsters. But they are made for running on the back of a quad bike and seeing how it all goes. And yeah, get a lot of positive responses from people. Some people made a lot of money. Believe me, they have made a lot of money. But yeah, and if you're going to do that too with big drag coils and things, you don't need a fancy doodah detector. You just use an old, because of the nature of the beast, you can use an SD2000. Okay, you can. There's going to be probably an advantage of using one of the older detectors than one of the newer ones. The older ones, an SD2000, for instance, is probably on big gold deep, probably the deepest going detector there is with a big coil. And that is my personal experience. I found some big gold using big coils and those old detectors back in the day. And yeah, like I say, the basic building blocks of all the detectors are basically in those old designs, and you can modernize them. Well, that's what we do. We modernize them. So you can, yeah, hook those up with your quad bike and your big coils, and you'll know when you go over a big piece of gold. You will know. So the only trouble with the SD though, you've got manual ground balance, but you know, if you're doing huge amounts of land, most of it's the same, like over in WA. Shouldn't be too much of an issue. And even if the ground balance goes out, does not, you may pick up more ground noise, but a big piece of gold is not going to be obscured by the ground balance being slightly out. Small gold will. You can tune it out. Big gold, no, it's going to sing through that. It's better if it's ground balance. It gets rid of the noise, of course, but it shouldn't really be an issue. So if anyone's done that over in WA and used an old detector, maybe you can make a comment about how manual ground balance goes whilst using a drag coil and a quad bike or motorbike even. People use motorbikes. They use all sorts. I've even seen people make a harness and walk with them, dragging it through the goldfields or any areas over there. You just drag it anywhere through WA, you'll probably find gold, that sort of place. But anyway, that is my waffle for today. I hope that's been educational. As time goes on with these detectors, I'll probably be, yeah, you know, we're going to get more and more into it. And, you know, there's going to come a time when I'm going to say, guys, this is how you mod your own detector. Here, you get this, you get that, and this is how you do it. Use this company, use this order number, get the boards. What? I've already designed and have come. And maybe, I don't know, maybe I'd sell them as kits. I don't know. One day, not at the moment though, not at the moment, because yeah, we're not at that point yet, but it'll come. It'll come, for sure. It'll come. Now, I've nutted out a hell of a lot of 6000s and 7000s. I've done all the, well, basically, I'll tell you how you do it. You get a good working one, right? And you need two people to do this. Get your oscilloscope. And what you do is you take a photograph of your oscilloscope on every test point in the detector. Okay? And you label it and put in a book that you have the waveform for every test point. And when you get one that doesn't work, what you do is you then have an idea what it is. So you know where the test points are. You just get, it's just, if you do electronic repair, it's intuition. You just know where to go. And you go, poke, poke, that's wrong. And then you work back and fix it, right? So, yeah, thank you, Minelab, for labeling all the test points. It comes in really, really handy. So it's not, yeah, throw your hands in the air. Oh, it's too complicated. No, you can work it out. Basically, most of it's repairable, except when it comes to that handshaking business, which is all encoded in the main, yeah, you know, FPGA type chip, the main CPU, and you know, maybe it loops in and loops out again into another chip. I haven't examined that yet. Might have a little oh, what do you call it? I can't remember the name of the chip. Like a little watchdog type thing. Not really a watchdog. It's like a little prom where it does a comparison and talks back to the main CPU. I don't know. I'll have to get into that, but I don't want to go too far in it and somehow decode it and say, oh, you don't need that. And you just put that there and it works. Did that for car radio once. Good old Fujitsu 10 with their coded car radios. They would not give me the code for the radio. I had the serial number, I had everything, the vehicle it went into. They absolutely refused. This is fact. And what I did, I had a look inside the radio and I went, da 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 da. And I said, hang on a second. That over there looks like goes in here, goes back round. Hang on a second. I got a 1K resistor, and I went bang. The bloody display turned on. So I just put a jumper wire across, and I knew how to fix those radios. Didn't need code after that. But yeah, yeah. So don't be cheeky. So, dear me. You know, who knows? It might have the same thing in these detectors. Maybe, you know, the 1K resistor trick, and see if we can loop it, get it around. I don't know. Maybe it has. Maybe it hasn't. And I tell you what, if I did find something like that in those detectors, I wouldn't tell my own mother. I'd tell no one because that's just pushing the limit. So, because I know what would happen. All our coil manufacturers in Australia would be out of business. That's what would happen. And we can't have that, can we? We want to protect our businesses here, what we got left of them. So, yeah, but it is possible. I don't know. Like I say, if I was an engineer working on something and I wanted a quick way of powering the thing up without jamming a coil or a dongle on it or something, knowing me, I would do that. I would say, well, if I connect test point 501 to 202, that actually will get around that handshake and turn the detector on. Possible, but I don't know. Anyway, I should shut up about things like that because now all the Chinese will be there with 1K resistors going like this all over the detector. I hope not, but you never know. And you never know, even in certain parts of that circuitry, maybe it's very sensitive CMOS and you're going to shove too much voltage in there, even through a 1K resistor and blow it up. So there, on you if you do it. You blow it up, bad luck. Anyway, that's that. I better get into this because I'm just going on waffling. I've got more units to do, and I've got to get this one done, and I've got some more to do. So I'll kill this, and yeah, get into it. Look at that, a whole hour of waffle. Anyway, catch us, guys.